Okay, the Doppler effect. The Doppler effect is a shift in frequency caused by movement, okay? Now, there are two ways I can shift the frequency that an observer hears. We're going to talk about two things here. We're going to talk about f of s, that's the frequency of the source. That's a frequency that's being given off, okay? Might be a siren, might be a whistle, might be something from a speaker. F0 is going to be what the observer hears. Now, if the source is moving, that's going to shift the frequency that the observer hears. If the observer is moving, that's going to shift the frequency also, okay? So we're going to have a few different things that we have to be careful with. First of all, V represents the speed of sound. Has nothing to do with the motion of the objects. Speed of sound just depends on the temperature of the air in most cases, okay? So that's going to be fixed for the problem. We're also going to talk about two other speeds. The speed of the observer, okay? How fast is the observer going? And the speed of the source. Okay. Just remember those, that there are three different speeds that we've got to worry about. How does this work? Okay, Doppler effect is experienced whenever there's relative motion between a source, that's what's giving off the sound, and an observer. When the source and the observer are moving toward one another, the frequency is shifted to a higher frequency, okay? That means that the observer will hear a higher pitched sound. When the source and the observer are moving away from each other, it'll shift to a lower frequency. That means, again, the observer will hear a lower pitch than is actually given off by the source. We can see how this happens. Imagine that we have a source of sound, okay? Located right here. If it's not moving, all the wavefronts are spaced out equally. However, once it starts moving, okay, it says source velocity is u. We're going to call this Vs. What happens is each point at which it gave off of a wavefront is going to be different, okay? That means that the most recent wavefront will be further to the left than the wavefront that was given quite a while ago. What happens there is the waves bunch up in front of the moving source and they stretch out behind the moving source. So we go from one wavelength, okay, lambda, to a new wavelength, which is much shorter. If the wavelength is shorter, the frequency that the observer hears is going to be higher. And we can actually see this in a ripple pool. This is a little needle which is going up and down into the water. It's actually moving in this direction. You can see the wavelengths are shorter in front and longer behind. There's Doppler shifting. Okay, let's do observer toward a source, okay? We showed that when the source is moving, the wavefronts bunch up in front of the source and stretch out behind, okay? But we also have to include what the observer is doing. If the observer is stationary, each wavefront will arrive at the observer depending on the speed of the wavefront and the distance between wavefronts, okay? But what happens when we're moving? If you're moving forward, you're going through each wavefront faster than if you were just stationary. If we're going through each wavefront faster, the frequency is higher. So we can say, if I go toward a source, the frequency will go up. If I go away from the source, now the wavefronts are chasing me, okay? They're going to take longer to go past me. The frequency will go down. Okay? So here's what the equation looks like. We're going to just say that the source is stationary, not worry about that yet. And we see, well, it's really quite simple. if you want to compare what the observer hears as they're moving compared to the frequency that the source gives off, it is V. Remember, V is always speed of sound, speed of sound, usually around 343 meters per second. Okay, it's there, it's there. But the observer speed, okay, gets plugged in right here. Now, the frequency goes up. This sign right here is positive if we are moving toward the source. Okay, we're going to shift the frequency up. We're going to hear a higher frequency. We change that to a negative when we're moving away from the source. Okay, so that again shows the effect that the observer has and their motion on the frequency. Now again, if the source is in motion, we get the wavefronts getting shorter in front and stretch out longer behind. Okay, smaller wavelength, higher frequency. How does that affect our equation? Now, if I keep my observer stationary and move the source instead, here's what happens. The denominator of the equation is affected. Again, just remember, V is that 343 meters per second or whatever the speed of sound is. Usually it's given for a problem where you figure it out from the temperature. But now, if the source is moving, okay, we're subtracting this off. The source is moving toward the observer, we subtract off. That makes this denominator bigger, smaller, which makes the frequency higher. Okay. We can combine both effects this way. The frequency that the observer hears depends on the speed of sound, depends on how fast the observer is moving relative to the source, and how fast the source is moving relative to the observer. Okay? Now, if the observer is moving toward the source, plus goes up here. If the source is moving to the observer, minus goes down here. The observer is moving away, we change the plus to negative. If the source is moving away, we change the negative to a plus. All right, let's do some examples. Oh, here's an application, by the way. We use ultrasound to look at the relative speed of the blood flowing through different capillaries. And this can see if we have obstructed blood flow. If an artery is blocked, we would generally expect that the velocity would be much higher due to the blockage. Okay, if it's not completely blocked. If it's completely blocked, you're in a lot of trouble. But if it's partially blocked, we could see the change in velocity and use that to diagnose a blockage. Okay, so here's an application. An ambulance is traveling down the highway with a speed of 33.5 meters per second. It's emitting a siren sound at 400 hertz. It's rather low for a siren, but we'll accept it. Assume that the speed of sound is 345 meters per second, okay? Approaching at 55 miles per hour is a car traveling at 24.6 meters per second, okay? What is the frequency as it approaches? What is the frequency as it moves away? Okay, so let's diagram where everything goes. The ambulance is the source. So that goes in this part of the equation right there. The speed of sound is V. So that's where that goes. The observer, that speed goes there. And here's the frequency of the source. Right there, lots of arrows. Okay? But that's where everything's getting plugged in. So we'll do the car approaching the ambulance first. All right. I keep a positive sign up here, a negative sign right here. I don't change anything because in this case, source is moving toward observer, observer is moving toward source. Okay? No change in sign. I plug in my speed of sound. Those go there. I put my observer speed in. My ambulance is going a little bit faster. And just do the math. Okay? 370 over 311. I get a ratio of 1.19. I multiply that by the original frequency. And as expected, the two are moving toward one another. I expect a higher frequency, a Doppler shift up in frequency. Okay? Now, by the way, you can have the observer move away from the source while still having the source move toward the observer. Let's say you're both in the same lane and the ambulance is overtaking you. Okay, you should really pull over. But if you're still moving, you're moving away from the source. So I'd have a negative on the top and the source is moving toward you. So I would keep the sign in the bottom. But again, in this case, it's plus and minus. Now, once the ambulance passes, both vehicles are moving away from one another. Now, in this particular case, the car is moving this way, the ambulance is moving this way. So I'm going to change my signs here from positive and negative to negative and positive. See what I do down here? Negative and positive. Redo the equation. Now I get a ratio less than 1, and the frequency is dropped to 338 meters. 338 hertz. Okay? So again, this really demonstrates how Doppler effect works. All right? You've got to consider the motion of the observer, got to consider the motion of the source.